I guess I should probably get my my laptop out, huh? Remind myself what it is I'm supposed to cover next. I think I remember, but let me get it out. Just every so often, if I look at my notes after the class and then I'm like, completely neglected a particular thing or something, you know. But try not to do that. On the other hand, I'm trying to let the Spirit lead me, and if I think of something new to say here, I'll say something new too. There is a, from a linear algebra perspective, there's something here that I've always wanted to do that I've never quite done. But anyway, more on that once I get started. Let me begin with a word of prayer. Dear Heavenly Father, we thank you for this class. I thank you that we have this time and place to talk about math together, and I just pray that you be glorified in what we do, and that we would just take each moment, Lord, and remember to stay focused on you in whatever we're doing, Lord. In my prayer, Lord Jesus, amen. Where is it? I guess we're in my advanced calculus notes, and so I have defined, so we talked about bilinear maps last time, right? And I talked about symmetric and, symmetric and anti-symmetric maps, and it probably would be good for me to do a calculation. I hate to erase anything. Yeah. Let me address the different kinds of bilinear maps briefly here.
You're still in 2015.
What's that? 2015. Yeah, I'm in the 2015. So I think I'll just erase most of this. All right, so I was going to at least talk a little bit about the coordinate change properties, if you will, of the matrices that define these maps, if you will, because there are a few different options we could think about. Yeah. So I'm just going to stick. I mean, there are more options but all right. So we already talked about last time. We talked about like B, an element of the bilinear maps on, say, VV, right? And by that I mean B is a mapping from V cross V to the reals, right? And the formula we had is basically just this. B is equal to the sum over I and j of Bij EI tensor EJ, right? That was it. Where Bij is literally B of E sub I, E sub j, right? Where we're using EIs and EJs for the basis of the vector space, right? Now, so if I had E bar, right? If I had E bar I, and that was equal to, let's say, for instance, like P I upper j, let's say, of E lower j, then we could also write that like E lower k is equal to P, let's see here, I guess we could use a Q for the sake of discussion. Q lower k upper, j, use an L, E bar L. And I'm not using the Einstein summation notation in here, so I need a sum over j there, and I need a sum over L here, okay? Sorry. And so, and of course, if you plug one of these into the other, you can see that, like, if you have the sum over, you know, P I K Q K J, you get Kronecker delta Ij, right? And I mean, I want to write it like that. I'm resisting it, but you kind of want to write it like that for, like, conservation of indices or some such nonsense. Notational scheme. Anyway, with respect to these, you know, notations, these coordinate change matrices, if you will, you can then study B bar Ij, right? What that would mean is B of E bar I, E bar J, and you can contrast that and compare it to Bij. How is it related, right? All right, so we get a sum of, you know, Pi, let's say K, and then PJL, and of course this is the sum over K and L, and then I've got my B, EK, EL, right? Which, of course, is literally my definition of BKL. So there it is in a nutshell. The coordinate change would be like this. Bij bar would be equal to the sum over K and L of P, I, K, P, J, L, B, lower K, L. Okay? There's the coordinate change rule given my notations established here at the moment, where I've defined my P and my Q matrices as such, okay? Again, Q is actually the inverse of P, truth be told. But just to unclutter things, I'm introducing a Q rather than a P inverse. I may regret that choice. All right, let's go on. Let me not belabor this too long. This isn't that interesting what I'm doing at the moment. So, another, I'm going to erase this right here. So what else could we do? We could also look at example 2. We could look at, like, B, an element of bilinear maps that go from V to V dual. All right? And so there we'd have a formula something like B of X comma alpha, you know? And that would be equal to the sum over I and J of X upper I alpha lower J B of E sub I comma E upper J, because I build the X with the basis with the lower index, and I build the alpha, the dual vector, with the dual basis, like that. And in this kind of context, we would define this to be the, you know, the component of the form, and we'd probably use this notation, lower I upper J, right? Like that. That would be the definition. And then here, if I was to calculate, you know, B, I'll try to squeeze it in. I guess I'll put it here. Well, B bar Ij, it would be equal to, you know, B of E bar I, comma E bar upper J, which I can get to the point here. That's going to be a sum over K and L All right. But this time, I pull out a p from the e lower I, just like before, right? I pull out a p I upper k, but then I pull out a q, right? And I guess my notation apparently is weird. Oh, phooey. My bad. I haven't yet discussed how the I need to show you how the dual basis transforms, yeah? That's a question. I haven't, that's a question. Right? How does dual? Change coordinates. And what I mean by that is, if we do a change of if we change the basis, right? So I've replaced, you know, I've got e bar I is equal to the sum, right, over j of, by my definition, p lower I upper j, right, e lower j. And what else do I know? Well, I know by definition that e bar I times e bar, let's say, k, that's got to be like Kronecker delta ik, right? And maybe I should begrudgingly, I will admit that it's probably helpful to do this here in terms of an organizing principle, but it does, I don't know. Anyway, all right, fine. The thing is, all right. But I can also say that e bar k, right, on e bar I is equal to Kronecker delta ki, right? Because there, I suppose I'm using the double dual in some sense. Well, am I? Maybe I was already doing that in the step above, right? I'm a dummy. Oh, I'm sorry. This is, I should write this anyway. Duh. I'm sorry. Like, there's no double dual going on here. It's just me being a dummy. Okay, let me get that out. Get that out of the picture there. Okay, so, all right. Well, we have e bar k, right? Is, you know, well, let me get to the point here. We can pull the sum out over j of p I j, and then we've got e bar k acting on ej. So what I did was I plugged in this into the formula, okay, I mean into there, and used the linearity of the dual basis. All right, but on the other hand, what else could I do? I could write this. Now this is just, I need to be sneaky here. I'm trying to relate the dual basis in the bar system to the dual basis in the regular, in the initial, you know, the dual to the original basis that we picked, which I've just called E1 through En. So if I can convert this to like a dual vector acting on something, that could be helpful. So let's see here. This would be equal to, well, as I just said, Kronecker delta ki. Rats. Man, that sum over j is just not helping me. All right, let me stop trying to be clever and let me just say we have this. Let us propose that E bar k is equal to a sum over, let's say, L of M. All right, and I guess I'll do KL EL. Just there has to exist such a matrix because we do have a dual basis theoretically to the barred basis, right? And of course we have a dual basis to the original basis as we defined last time. So there's such a matrix has to exist. The question is, how does that relate to my P and Q matrices? Because I'd like to have everything in terms of P's and Q's, where Q is the inverse of P actually. Okay, so if I take this, right, and I act on EJ, what do I get? I get this, right? Which is Kronecker delta, LJ, which kills that sum over L and replaces it with simply what? M M sub what? M sub, I mean, M upper K lower J, right? So in view of that, I can come up here and say, okay, what I have is I've got the sum over J of P I J, and that is in fact M upper K lower J. Dang it, I erased the one stupid thing I needed. I had an equation right here, which would all I wanted, you know? And so that equation was this. The sum over, let's say, J, I guess I'll do sum over, I'm going to make it match the index structure here. Sum over J of like P, I, J, Q, J, K equals Kronecker delta IK. So if you look at the fact that this matches that, and this matches that, and since P is invertible, you can read from this, since the inverse is unique, it follows that, right, this guy right here has to be that guy right there, right? So in short, although I took my sweet time getting to it, we have a theorem, if you like, and the theorem is simply this, which is that the dual basis E bar E bar I is equal to a sum over J of Q. Let's see here. I guess it puts the J here and the K there and the I there in my notation. Because of the way the indices are flipped around in my... All right, so now that we've got all that, finally, E bar J is Q. I put my index of summation first, L and I put my free index j second like that, and then I've got myself a b lower k upper L. And there you go. That is the coordinate change rule for a bilinear map on V cross, you know. Like that, right? I'm scared to erase this portion of the board, but I need to. Okay? Are you good? You have it, okay. So if all right. That formula up there is key, I suppose. All right, so there are quicker ways to derive this for sure. I mean, if you just kind of look at the fact, the easier way to derive it is something like this, Ernesto. It's something like this. EI, EJ is Kronecker delta IJ, right? But that's also equal to E bar I, E bar J, right? So just intuitively speaking, however the dual basis transforms, it must transform inversely to the basis. Otherwise, you can't have them both agreeing on the Kronecker delta. You know, so whatever, like intuitively, whatever change there is in this, it has to be balanced by change in that. So that would have been much faster than what I did, but I have no regrets. I mean, it's good for us to go through the calculations as we did. Example 3. If we had B is a mapping from, say, V dual to V, bilinear, right? So B is an element of, in my current notation, V dual, comma V, then we would have something like B of alpha, oh, that's my bad, V cross V to reals, dummy. So B of alpha comma X would be like, you know, sum over, say, I and J of, it would work out to alpha sub I, X upper J, and then B upper I sub J, where B upper I sub J is by definition B of EI and then lower EJ. And if we change coordinates, right, B bar, IJ, how's that going to go? Maybe you can start to see the pattern. We need a P for each lower index, and we need a Q for each upper index. So it's going to be like sum over K and L. For the upper index, I need a Q. And I do the summation first and the free one second. And then for P, I do the free one first and the summation one second in my current notation. And then I have B, let's see here, upper K, lower L. And that would be the coordinate change rule for a bilinear map on V dual cross V, okay? And then example 4, finally, we'd have what? We could have B an element of B basically a bilinear form on V dual. So here B would go from V dual, Cartesian product V dual, to the reals. And so my formula would be something like B of alpha beta would be equal to like sum over I and J of alpha sub I, beta sub J, B upper IJ. And B bar upper IJ would be equal to a sum over K and L. This time we get Q's all around. So we've got Q sub K I, Q sub L J, B sub, whether it be upper KL. And that would be the coordinate change rule for a bilinear map on the dual. So the way the change in coordinate works here is it's always based, it reflects our index convention. You see, if we have an upper index, we transform one way. If we have a lower index, we end up transforming the other way. And there's a general like pattern here and rule that affords, that's part of what is making this up-down index notation a reasonable enterprise. If there was no kind of rhyme or reason to the coordinate change as it related to the up-down indices, then this would be much, much worse in terms of like keeping track of. But there is an organizing principle here. Now, the other thing I should talk about is there is a natural relation between bilinear maps and like this is something I forget about, but let's work it out together. Suppose we have a linear map from V to V. How would that fit into this current story we're telling? So here's my question is, can you tell me how would we, if we want to talk about a linear transformation T, linear transformation from V to V, okay? Can you tell me which, if any, of these four examples we could kind of use to... Oh, and I never sent you the homework the other day. I'm sorry. My office hours were just jam-packed. I can't think once I get in there. And then when I got home, I don't know what I did. Nothing profitable. I guess I slept eventually, but I should probably sleep more. Where was I? Okay, so linear transformation, right? Can we write the formula for that using the dual basis and all this jazz, like stuff, right? Like, think about it. T of x, right, is T of the sum, right, of x upper I, e lower I, right? That's one thing that's true. So I can write that as like the sum over I of like x upper I, T of ei, right? But on the other hand, T of x is an element of V, right? Thus, T of x we can write as a sum of Tx upper I, ei, right? But we can write that like this. And maybe I should use a j here since it's probably going to be a different summation idea here. So I can rewrite that as the sum of ej, right? Acting on T of x, because that's how to get the jth component of the vector. Right? The dual basis is the jth component of the whatchamacallit there, the coordinate map, right? So I have this expansion here, and let's see, can we? But of course we can do what I did up there down here and pull it out, right? We've got sum over I, j of like x upper I, and then e upper j of t of ei, ej. I feel like I'm forgetting something here. I mean, it's not the formula's fine. It is what it is. Excuse me. It is what it is. And of course, excuse me, we would probably call this like, you know, AJI or something like that, or maybe AIJ in their current notation. And oh man, I just don't, I hate to. I'll write it this way: A upper J lower I. So I've got, you know, this. If I write that, then I can rewrite this as like the sum over I and J of like, you know, A J I X I, you know. Like that. And anyway, you can see how the coordinate changes, right? Like what's A bar Ji? Well, it's E bar J T of E bar I, right? And in my current changed notation, my dual basis transforms by a Q, right? So I get like a Q, K and then J, and this guy changes by a P. I and then L, and I got myself an A, K, L in my current notation, I believe. And of course, you could look at this as like the sum over K and L of Q, K, J, A, K, L, P. Well, maybe I should go the other way. P, I, L, A, K. I mean, I don't know. I'm not been quite careful enough about all the conventions here to have things sorted out exactly with confidence. But this is basically the coordinate change relation we found for the matrix of a transformation before, if we're changing the basis on a vector space, right? Which was like we have P inverse AP for. So P inverse kind of. This is a matrix multiplication by a matrix and its inverse. That's the coordinate change for the matrix of a transformation. So like we can put these things together with our previous coordinate change discussion if we want. If I had all my, but there I was definitely not doing up down index stuff. So we'd have to, in a perfect world, I would find another couple hundred hours to make uniform all of the notation throughout the course and, you know, fix things nicely. But I just I find the up down stuff to be distracting when we're not talking about it. You know, like it just makes things harder for students if I introduce it too early, even though it would then be more logically consistent later in the course. So it's like, you know. All right, so anyway, this is quick tour of coordinate change for bilinear forms. And the other thing I should mention is, so for a symmetric bilinear form on V, we have basically B of x comma y is equal to B of y comma x, right? But notice what that means is that I have an identity that B of x comma y is equal to like 1/2 of B of x comma y plus B of y comma x. I mean, that's true. I could say that. And if you look at the formula for it, right? This is the sum over, say, I and j of, let's see here. Oh, rats. I'm sorry, I don't want to commit to what I'm doing. I should be committed. No, that's not the way I want to do it. Let me just start with the formula. So what's the formula for the bilinear form generically? We've got something like b of x comma y is the sum over I and j of x upper I, y upper j, bij, right? But you could I guess it's not too interesting here in some sense, but I can break this into a sum, right? I can do the sum I less than j of you know, xi, yj, bij, and then plus the sum I equals to j, right, of xi, yj, bij, and then I can do plus the sum of I greater than j of xi, yj, bij, right? So I'm not saying anything terribly profound. I'm just saying if you've got a double indexed sum, you can split it into 3 cases, right? I less than j. And so like if you want to look at it sort of pictorially, right? If this is I and this is j, and here's the diagonal, right? I equals to j. I less than j, I guess, would be like these ones down here, right? And I greater than j would be the above the diagonal in terms of like if you're looking at index pairs, right? So that'd be like these guys, and that's in the middle. Now, for a symmetric bilinear form, bij is equal to bji, right? So what I can do is well, let me just relabel both sums. The first sum I'm going to relabel with k and l. So k less than l, x upper I, x upper k, y upper l, bkl, plus the sum over I of xi, yi, bii. All right. Because why not? You know, okay. And then plus, now here, on this one, I'm going to make a different substitution. So this one I made I equals to k, j equals, this one I'm going to do I equals to L, K rather. I'll get it eventually. The other way around. I want to let I equals to L and J equals to K for this one. So if I do that, what does this summation become? If that's the case, I greater than J becomes what? L greater than K, also known as K less than L, right? So with that substitution, then we have the same index structure on this one. However, it does come at a certain cost. That becomes x upper L, y upper K, right? That's different. And then, of course, we also have b sub K, LK here as well, right? But b sub LK is equal to b sub KL. So I can use that, and I can combine these two. And what I have then is a sum over K less than L of BKL of XKYL plus XL k, right? For the outer sums. And then of course we still have the middle guy. Then, if you look at this, we can write this as the sum over k less than L of BKL times EK tensor EL plus EL tensor EK plus the sum over I, let's say, of BII, EI tensor EI. All right. All of that acting on x comma y. And you might introduce a notation like, let's see here if I have this in my notes. I probably don't. I'm just going to try to be consistent with whatever convention I chose in the notes. Okay, so I did not put a combinatorial factor in. Some people put combinatorial factors into the... all right, so anyway, here, getting to the point. This is, we could define EK... This is, you won't find this in too many books, but this L to be EK tensor EL plus EL tensor EK. And in fact, if you look at that, what does that say about EI symmetric tensor EI? Well, it's just what? Oh, my bad, it's 2. Oof. Man. Man. Oh, man. Oh, man. Well, anyway, that is what it is. But then you can see, like, this you can just replace with E, the symmetric tensor of EK and EL. Now, what if instead of symmetric, right? If instead of symmetric in this argument, cross out symmetric and put anti-symmetric, how would this change? What if I, said, oh man, well that one was dead, this one's dead. What if I put anti? That would just change what in this calculation? It would really just change right here. That would change that to a minus when I combine the sums, because we would have minus there. All right, and that would put a minus here. All right, and that would make this be 0, because BII is equal to minus BII, which means BII is 0 because we're in characteristic 0. So when twice something is 0, it's 0. Now, and then this is what we introduce. EK wedge EL is going to be EK tensor EL minus EL tensor EK. This, of course, is much more widely known and talked about. But the symmetric tensor is interesting for certain applications. I mean, symmetric tensors are not interesting, to use a stupid phrase. And so, just to summarize here, what we've calculated and shown is that for an antisymmetric tensor, we could enter an antisymmetric bilinear form. We could write this: B is equal to a sum over k less than L of BKL EK wedge EL. However, if you'd like, you could instead do a sum over just k and L. So that's a sum over all the indices. And you can rewrite this in simply as 1/2 BKL EK wedge EL. Which you could also write as the sum over k and L of BKL of EK tensor EL. So these are some different ways we have to express a antisymmetric bilinear form. So far, so good? Questions?
So the wedge is when it's antisymmetric.
Yes.
That's how
So-
we build tensor product. So we have that.
Yeah, so one way to build the wedge product is to antisymmetrize the tensor product. So yeah, all I've done so far is define the wedge product of two two dual vectors. Yeah, go for it. Now, of course, we would like to talk about more. We'd like to talk about, well, multilinear forms, right? And, well, we'd like to talk a lot more about the wedge product, but I'll suspend general comments about the wedge product until for the moment. There's so much more to say about it, but we haven't really defined it in its glory yet. So let's put that off for the moment.
Will we do that here in this class?
Oh, yes.
And here's serial algebra.
Yeah, we'll talk about the exterior algebra. That's really what we're about to get into. But we do have a little bit more just plain old multilinear algebra to talk about. And so here's the definition. If you have T mapping from V1 cross V2 cross cross VK to R, which is linear in each argument, then T is multilinear. Map on, V1 cross V2 cross cross. So VK, and it's technically it would be a K multilinear map because it's got K inputs. We talked about bilinear you could say it's a two linear map if you like. Okay. Now, I'm not especially interested in like the totally general, abstract kind of and multilinear map, and this is also known as a tensor, aka a tensor. So a tensor is a multilinear map. We're primarily interested in a more narrow context when we're really just looking at a tensor on, I'm trying to make sure I get my notation right here, so give me a second. Because there's some choices to make, all right? So
Which page are we on?
189. Come on. Just I'm looking for something. I'm not finding it. Of course, I have things on trilinear maps that I'm skipping over at the moment just to get to the general definition, if you're okay with that.
Sure.
I have a gory definition of trilinear map on 186.
Okay.
So it's very unsurprising. It means you have linearity in 3 slots, right? And I show that you can, build the formula for a trilinear map by a tensor product of 3 vectors or 3 dual vectors or a mixture thereof. But there are some examples in there. I'm going to go back through those examples. I'm not skipping the examples. I'm just reorganizing things slightly. I want to give the general definition here. Okay. So VR cross Vs. So I'm going to put T on V cross V cross V, R fold of these, and then cross V dual, cross V dual, cross V dual, S fold copies of the dual. All right, and it maps into the reals. All right. This is said to be a tensor, or it's a multilinear map, and then we'll say T is an element of T. My notation in the notes at the moment, hopefully, is an upper S, a lower R of V. It is a quote-unquote type. A type RS tensor. On V. Some of the older books used to say rank RS. That's not a good terminology because rank instead of type. I try very hard not to say that because rank has a specific and technical meaning in terms of linear algebra, which I'd like to be able to use meaningfully. And so I use the word type here to avoid that confusion. And so it's a type RS tensor on V if T is linear in each, input, either V or V dual, right? I mean, you have the V's, you have the V duals. It has to be linear in all of these, okay? And so this is what a multilinear map is, and also it's what we call a tensor. And so since I was talking about coordinate change today, let me do my evil all at once.
So why do we replace some of the V's with V dual?
Oh, just because that's the kind of object we're interested in generally, is it's going to have a mixture of inputs from V and V dual, depending on the context. Sometimes we just look at just V inputs, sometimes just V dual inputs, sometimes we just have one or the other, but I mean, of course, there are other things you could do. You could, for example, you could talk about a matrix valued tensor. You could place the real numbers with a matrix and you'd have a matrix valued tensor. You could put other things here and talk about blah, blah, blah valued tensors. You could do that. You could, of course, like I said, generically, just take k-fold copies of different vector spaces and have linearity in each. That would also define a tensor in the more general sense. But let me write a formula for this, because I want to talk about what are the components of the tensor with respect to a basis. See, so, and that will actually help me complete the definition that I'm not writing out, because I'm being lazy and not writing out the definition. Okay.
And R plus S equals K, right?
Yes, R plus S would be equal to K. That's a good point. Yeah. Indeed, there are R plus S inputs. Okay, so my vector inputs, I usually use like Latin letters. So I use like X. I guess I need to use I need to like enumerate them, right? So since I put the index on the vector up, I'm going to put the label down. If that's okay. So like X1, X2. I've got how many? I've got R of them. R. And then since I put the index down on dual vectors, I'm going to put the label up. So I'm going to talk about alpha 1, alpha 2. And again, these are, from V. And these are all dual vectors. All right, so I'm not talking about components here. I'm talking about vectors and dual vectors. Each one of those has an expansion either in terms of the basis or the dual basis. And to say that T is a tensor is to suppose that it has linearity in every single input, which means I can pull out the components for all of these. So I've got like a sum, and I'll enumerate them. I1, I2, IR. Sum J1, J2, JS. And I've got my X lower 1 upper I1, X lower 2 upper I2, X lower R upper IR. And then I've got my alphas. Alpha upper 1 lower J1, upper 2 lower J2, alpha upper S lower JS. Those are the components of the inputs, the vectors and the dual vectors. And then I've pulled those out of T. What's left in T? T of what? T of E. EI1. EIR. E upper J1. E upper JR. That we denote by this, we simply denote by T, I1, I'll do the 2 this time, IR, and then upper J1, J2, JS. That is the components of the tensor, T, with respect to the basis, the EI basis that we've been working with today, and I introduced last class. Then, of course, you can ask the question, what if we changed coordinates? What's the tensor change rule what's the coordinate change rule for a tensor? But we already know how to do this. It's simply what we already did today. We get a P for every lower index, and we get a Q for every upper index. You see? And so the rule would just be this. T bar, and I'll put some, I guess I'll use K's and L's. K, now in physics, they decorate the indices to tell you that the new indices are with respect to a new coordinate system. But I'll stick with math notation here for the moment. K1, K2, KR, L1, L2,